All right, today we're going to talk about the fundamental theorem of calculus and how derivatives and inverses are, derivatives and integrals are inverse-like. Even though derivative is slope and integral is the area, they still undo each other. So the first part of the fundamental theorem of calculus says that if you have a function that's defined as kind of an accumulation definite integral function from some number to x of f of t, then if I take a derivative of that, it undoes the integral and I wind up with f of x as the derivative. If I have my limit of integration is not just a plain old x, but it's a function, then I have to apply the chain rule when I do that derivative. So if I take the derivative of that definite integral, it would be f of h of x times the derivative of h of x. So an example of that chain rule situation is, well, maybe you recognize, oh, that's tangent inverse, but you actually don't even have to worry about that being tangent inverse when you take the antiderivative, because we're going to be taking the derivative, so we don't need to worry about taking the antiderivative. If I take the derivative of this, I get 1 over 1 plus 5x squared times 5. And then if I want to find g prime of 2, I just plug 2 into that, and I have 1 over 1 plus 100 times 5, so 5 over 101. The type of free response question that tests the first part of the fundamental theorem is one where you're given a graph of f of t, and you're given a function that's defined as an accumulation function. This particular accumulation function is going to start at 1, and so if I want to find g of 4, I'm going to accumulate the area between 1 and 4, so it's a triangle, so it'd be 1/2 times 3 times 1. If I want to find g prime of -1, that would be f of -1, and that would be 0. Sometimes I see people say g prime of -1 doesn't exist because they see that corner there and it freaks them out. But because it's a corner on f, it's okay. If we were finding a second derivative at -1, that would be a problem. Okay, second derivative at 0 would be f prime at 0, which would be 0 because there's a horizontal tangent line at 0. So if I want to write an equation for a tangent line to g at x equals -3, that means that I need to accumulate area from 1 backwards to -3. Since it's backwards, this area that's below the x-axis, which is a semicircle, so it has an area of pi over 2, is going to count as positive because it's below the x-axis, but I'm going backwards. And then this area of this triangle, which is an area of 2, is going to count as negative. So g of -3 would be pi over 2 minus 2. G prime of -3 would be the y-coordinate, so that'd be 2. And so my equation for my tangent line would be 2x minus 3 plus pi over 2 minus 2. Points of inflection for g, that's going to be when g double prime changes sign, or when f prime changes sign. So I notice that f prime is positive up until x equals -3, and then negative. There is a corner at x equals -1, but not a change in sign. And then x equals 0, there is a change in sign because the change goes from negative to positive. There's a corner at 1, but not a change in sign because it's still going positive. So we have a point of inflection that's at -3, comma, pi over 2 minus 2, and another one that's at 0, comma, pi over 2. I want to point out that there is a corner, so there G double prime doesn't exist at -3, but there is a change in sign, so that makes it an inflection point. The second part of the fundamental theorem of calculus says if I want to evaluate one of these integrals, then the integral can undo the derivative, so I wind up using antiderivatives to evaluate definite integrals. This fits with the idea that the integral and the derivative undo each other because it allows me to go backwards from the derivative to the function that produced that derivative. That is a quick review of the fundamental theorem of calculus. Oh, before I go, I want to point out that if you're applying this integral, this definite integral, it is the net change in f. So if you are looking for a net change or a displacement, you would do the integral of velocity because that gives you your net change in position. Okay, good luck, have fun.